All right, so again, we're talking about this equation because it's not simply an inverse relationship because there's some kind of a maximum value in asymptote that we're approaching that appears to be around 5 or 6. So with A equal to 5.6, pretty closely fit most of the data, though not right here in the middle of the run. And so that expression is known as the Thin-Lens equation. One over the image distance equals 1 over the focal length minus 1 over the object distance. And there are a couple other important equations for lenses that you should have would have encountered in the reading the other night. We're going to look at how these work a little bit too with diagrams associated with this stuff. Let's see. So with your Desmos lab, go ahead and fit it with this expression. See what kind of value you get for A. And then just add in a note with that. And you should be good to go there. So I'll give you a few moments to wrap that up, and I'll get some papers handed out your way. Next. You want to avail yourself of a ruler. Does that work okay? Cool. How long has it had it? We have located about 20 pesos. Putting more millionaires in Do you need time to collect more data? Yeah. We can find that for you. All right, the other thing I want to take a look at before I cut you loose for some work time today is image location by ray tracing. And I've not ever done this not on an overhead, so I don't know how this goes. We'll kind of just check it out, see what's what. I guess I do have an overhead. I don't know if I have overhead pins. So image location by ray tracing. And then I handed out an FRQ. It's an older FRQ. It's from a previous version of the exam, but some of these skills were used there. So you can see these points marked F, and they represent the focal distance or focal length of the lens. And these are really, really thin lenses, yeah? So I'm going to attempt to draw a line here right through that lens, okay? So such a thin lens that we're going to ignore that refraction is happening at both surfaces of the glass. We're just going to treat it as if it bends kind of in the plane of the vertical axis of symmetry of the lens. And then I've got everything happening on the line, the horizontal axis of symmetry for the lens. But we have here the focal length. So for the lens we just got done with, we would draw that at 5.5 centimeters. We'd put that dot, okay? And I'm putting it on both sides of the lens, and we'll talk about why that is here in a moment. So this was set up for a two-ray diagram, but I'm going to go ahead and teach you the third ray that the government doesn't want you to know about. Okay? So you want to grab a ruler here quick, sharpen up your pen or pencil.
I'm still like halfway.
And the first ray that we're going to take a look at is based on something we already did last week. You took a ray and aimed it at a triangular prism, okay? And it's parallel on the left side. And then you did a little bit of math to see that it's going to bend down towards some point on the right side. We didn't have a name for that yet, but there it is. It's the focal point. I'm going to skinny this up a little. So that's my first ray that I'm going to draw here. Okay, ray 1 is going to be parallel to the axis of symmetry on the left side. Let's put a T in left of the lens. So I'm going to start out here at the tip of the object, and this is where it gets a little squiffy because I don't have a ruler. But I'm going to attempt to draw, yeah, it's going to work really well. A ray that's parallel to the axis of symmetry there. Really, buddy? This or that? Oh, the heck with it. I can freehand this. I got skills. Okay? So it's parallel to the axis of symmetry on the left side. That ray is going to be bent through the focal point on the far side. And I'm just going to trace it as far as I need to go. So parallel to the axis of symmetry on the left side of the lens. Will pass through focal point on right side of lens. Okay. And I should point out, this is for a converging lens that this rule applies. Should probably make it clear that these are different rules for different types of lenses. Oh, come on, man. So converging lenses. All right, ray 1. Parallel to the axis of symmetry on the left side of the lens will pass through the focal point on the right side of the lens. Ray 2. So if we go back and look at some of our stuff, from earlier on, you sent a ray straight through the center, and it just kept on going in a straight line on the other side. Okay? If you look at the geometry of the lens there, the sides are parallel. And if you go back to when we talked about refraction and looked at this example in class, when the sides of the block are parallel, that ray is going to emerge on the other side parallel to the original beam. Okay? So light passing through block with parallel sides. And I guess it's kind of key that it's emerging into the same medium. Emerging into same medium as initial ray will travel parallel to initial ray. So I could kind of vary that angle that it enters the block, but it's always going to emerge, whatever this is, we're going to emerge roughly parallel to it. It's not the best diagram there, Mr. Harding. So the way that that's going to feature in a ray tracing is if you imagine a ray that goes right through here at the center of the lens, we have that same geometry, okay? The sides are parallel. So if I fire a ray right, it's poor. Try it this way. I don't know. There we go. That's not terrible, Mr. Harding. Okay. Ooh, other than I want to make that be blue. There we go. Tip. Make that blue. Perfect. Ray through center of lens. Nice if your penmanship wasn't terrible, Mr. Harding. Emerges. Wow. Emerges undeviated on the other side. Okay, so you can already see in this diagram that we've got this point of convergence right here. And that's where my third ray is going to come in. You can get two rays to converge pretty easily, but if you can get a third ray to converge, then you know you're in pretty good shape. So I'm going to take a ray and I'm going to force it through the focal point on the near side of the lens. And it's going to emerge on the other side. Let's see if I can do that ever so slightly better. It's going to emerge on the other side and travel parallel to the axis of symmetry on the right side of the lens. So this is my ray number 3. ray through focal point on near side of lens. That's a terrible travel parallel to axis of symmetry on right side of lens. And yeah, I kind of cheated because I'm not using a ruler, but you can see how that's going to put everything together here at this point of convergence. And so that's going to be the location of my image. So there's my image. This would be my image distance. And then on the other side, this would be the object distance. So see if you can figure out with that next diagram, what is the effect of moving the lens closer to the object? We have a smaller object distance. And then let's see what that does to the formation of the image there. And then I have to recognize that it's Tuesday. So we're Audi at 29. Good. Yeah. Jimmy J. Gordon. Goes with this stuff eventually.
Well, but look at the actual equation. Smaller.
So again, you're sending through your three characteristic rays. The first one parallel to the axis on the right. Actually, before I even do that, I'm going to draw my line right down through the center of this thing as best I can. There we go. So that's the plane where I'm going to have all the bending take place. I take this ray parallel to the axis on the left. That's going to be bent through the focal point on the right in the world's worst drawing. Try that again. There we go. Something like that. I'm going to take my second ray straight through the center of this thing. Try to keep that going constant. And then I'm going to take a ray, and this is where it gets tough. Make it go through the focal point on the near side. And that's going to emerge parallel to the axis on the right side. And so I get an image that is increased in size, but still upside down. Oops. All right. Any image that's formed by converging rays that are forced together at a point like this, is called a real image. A real image can be projected onto a screen or a card, just like we did in the lab. That's not always going to be the case. But in these two situations where the object distance is greater than a focal length for a converging lens, that's when you're going to form a real image. This gets a little different when we're dealing with objects that are very close to the lens. So I'm still going to try to draw my three characteristic rays here after I draw my axis of symmetry for this lens. Vertical, oh, that's poor. That's not going to get the job done, Mr. Harding. Let me have it. Nope. Try this again. Shape line. Man, it really doesn't want to draw that through there, does it? What's up with you? Bend to my will. Oh, there we go. Made it work. So my first ray parallel to the axis of symmetry on the left side is going to be bent through. Bent through the focal point on the far side. And then I'm going to do the other one where I send it through the center of the lens, and it's going to emerge undeviated on the other side. But you can see already what problem am I encountering here as far as image location. What's happening to my rays? They are diverging. The third ray is kind of a mess. This is why the government doesn't want you to know it. You've got to draw it as if it passed through the focal point on the back side here. And then I didn't extend this plane high enough.
Yeah, but it misses the lens.
Yep, so this is why I have this line here, this axis of symmetry. Just extend that up. That's where I'm saying all my bending is taking place. That ray is going to emerge parallel to the axis on the right side. Okay, so right now it's just a big hot mess, diverging rays. So although it's called a converging lens, you can make it produce diverging rays. That's why I think the term convex is preferred. What I now need to do is trace all these diverging rays back behind the lens on the left side. So this one's pretty straightforward. I'm just going to trace that back parallel to the axis of symmetry. Boy, this is going to take some doing here. Oh, I wonder if I can. Oh, there we go. That's clever.
I use a lure to make that ray, and it goes up, and the point where it intersects with that line goes up.
I believe it. So I'm not doing great here in terms of my convergence. What's up with that? I'll do these better. Aye! Coming off together, that's not great. Oh, use the tool, donkey. There we go. Whoa. All right. Maybe it's because I drew the screen one so crap. Maybe that's the issue. This is kind of what Gavin was saying, right? So if I were to actually trace this up, it wants to be even higher up the page.
Yeah.
Okay. Close enough for government work, right?
There's no actual lake.
So a little easier to do this with rulers on paper, but back here, we can draw it, is the point where the rays appear to have come from. So it seems like the light came from there. So this is our image. Clearly, we would say the image is enlarged. The image is upright. And in this case, the image is virtual because this point of convergence doesn't exist. The light rays were never actually at the point that we're calling the image location. So image, distance, object, distance. So this is how we get that magnification to work. So the image is located behind the lens when you're using it as a magnifier, and it appears larger to your eye because of the way that the lens is making the light spread out.
But you also see less. You also see physically less behind the lens because parts are pure by
Zoomed in.
converges away from your eye.
All right. The last one then, diverging lens. The rules change slightly. So this is going to be image location by ray tracing. By ray tracing. But now we're dealing with a diverging, aka concave lens. The rules are somewhat similar in that ray 1 is going to be drawn parallel to the axis of symmetry. I keep forgetting to put the damn boop line. All right. So I'm putting that vertical axis of symmetry through the lens. That's where I'm going to make all the bending take place. I'm going to draw parallel to the horizontal axis of symmetry on the right. Because it's a diverging lens, instead of bending towards the focal point on the opposite side, it's going to diverge. It's going to spread out as if it came from the focal point on the left side. Okay? So ray parallel to axis on the left bends as if it came from focal point on the left. The easy button is the ray through the center, because again, in the center of this lens, just like the other one, the sides are parallel. Oh, if I could only draw it. Okay. So ray through center of lens. Emerges undeviated on the other side. And then my last ray, ray 3, I'm going to aim for the focal point on the far side. This might take some doing here. Yeah, poor. That's already poor. There we go. That's not terrible. So it's going to be a ray aimed towards the focal point on the far side. Boop. And it's going to bend and emerge parallel to the axis of symmetry on the right. So if I trace this back, you can see where our image location is going to be. So ray 3, ray directed towards focal point on opposite side of lens will emerge parallel to axis on that side. All right, we'll finish up with that business tomorrow and work on that FRQ in class.